You asked me if an ordinary person, by studying hard, would get to be able to imagine these things like I imagine. Of course.
Hello, hi guys. Welcome again to the second lecture. And again, I'm Myke. And in the first lecture, we talked about what is a database, what is the DBMS, flat files, the difference between flat files, and the Stroma idea, the flat file, and then the shortcomings of the Stroma idea, and then we talked about the guarantees of the DBMS, right? So just a quick recap. Let's go through these things together again today. So yeah, in the last lecture we talked about database. What's a database? We talked about that database is an organized collection of interrelated data that models some aspect of the real world, right? And then we talked about DBMS, right? The DBMS is so yeah, let's type out so you can follow me and all. So a database is an organized collection of interrelated data that models some aspects of the real world, right? So that's what e.g. hash table, we talk about hash table, we talk about your journal and all, right? So this is just a quick recap. About first lecture. So we talk about the journal at the end, your journal, your notes and all, your notes, phone book, etc. Right? So these are databases. These are examples of databases, right? And then we talk about database management system. Database management systems, right? DBMS is a software, right? It's a software that manages the content in a database, right? So that's what a database management system is. I'll talk about Postgres. I remember we talked about Postgres. We talked about Apache Pinot. We talk about Apache Pinot. ClickHouse, etc. MySQL, MongoDB, etc. And etc. We talk about the flat file, the issues with the flat file. What are the issues with the flat file? Issues with the flat file. We mentioned data integrity, right? Data integrity. Anybody can write anything on any line, right? There's no strict rule because it's a flat file, and that's one of the issues, right? And then we talk about concurrency, and then durability in such a way that if you are trying to write to this data, if you are trying to write to this file at any point in time, but if there's a power issue or anything that's going on, that means that we'll lose most of the file, what we are writing to the file. So these are the issues with the flat file. And then we talked about the guarantees of the DBMS. We talked about atomicity, consistency. We talked about isolation, and what? Durability. So this is what the DBMS guarantees to us that, okay, if you are using a database management, if we are implementing a database system, or we are using, right, we have to ensure that these guarantees are in place. And then what atomicity is telling us is that if I tell you, if the database management system, you are writing this record into the database, I will ensure that it is either written or none is written into the database. That's what atomicity is telling us. Consistency is telling us that I will ensure all your rules that you enforce, right, on any right is enforced even at the database level. On flat file, we have to do that on if you're using a flat file or something that does not guarantee consistency. That means you have to enforce it on the application level, which is not what we want to do. Isolation is telling us that, okay, if you're having two or three threads, line of execution, or a user or 2 or 3 users are trying to update or do one or two things on the same record, right? It ensures that they are done separately, they are done differently. That's the meaning of isolation. And then durability is telling us that if anything is going on with the database, any power cut, system crash or something like that, I can get to that state. I can get to the original state of the database, of the of the current state or the original state of the database. That is what durability is telling us. And yes, so today we'll be talking about data models, right? So today's agenda, data models. Data models. What are data models, right? We use models, right? So let's say that the data model, this is a set of concepts, right? Concepts that describe the data in the database, right? So when it comes to structure, the way it is structured, the way data is structured, this is what we are talking about, data model. And also we have different types of data model, right? We have relational data model, right? Everybody knows that relational data model. We have graph, we have network, we have key value. So type of data models, types of data models. So we have one, we have relational. This is the most popular, right? When you're talking about MySQL, PostgreSQL, and all, this is what we're talking about. We have key value. Key value data model. That's where we talk about Redis, memcache, etc. Right? So these are key values. And then when we talk about objects, documents, right? Objects, document. We talk about stuff around MongoDB, CouchDB, etc. Right? We have them like that. We have network data model. We have this is 4, and then 5. We have graph data model. So a database that is model around this model is Neo4j, right? Neo4j is a graph data model. And then we have vector, matrix/vector. We'll talk about these things as we move along in the course. Vector. So these are machine learning, right? They're using machine learning DBs, right? So so these are the types of data model that I'll talk about. And before we talk about I want to talk about the early DBMS, right? What's early DBMS? So this is just early DBMS. What are the challenges, right? What are the challenges in the early DBMS, right? Database management system. What are the challenges, right? One of the challenges is that early DBMS, early database management systems, they make it in such a way that the logical layer and the physical layer are tightly coupled to the application. So physical and logical layer of the DBMS is tightly coupled together. So that means that you have to ship the DBMS with the application, right? So if you're writing an application, you have to deploy it for that specific application. If anything change in your database model, you have to redeploy the database. That's strenuous. That's issue. That's not what we want to do, right? So that's not what we want to. That's not what we want to do, right? They're tightly coupled together. So which means if you are you write a specific DBMS for a specific application, right? If the requirement database data models relations, you have to redeploy the database and make changes to the application, right? Imagine they're tightly coupled. That means you have to change the application, change the database, right? That's not what we want to do. We want it to be like separation of concerns, right? The application, if anything is going to change on the database, we allow this to change on the database, and then the application can still function without having to, changing a lot of stuff. And that's where so now right now we have to talk about a little bit of history, right? That's where third called Edgar comes in. The third called Edgar. So this is IBM researcher, mathematician. This is a mathematician. So mathematician, IBM research lab. So what did Ted called Edgar is talking about? Notice. You notice that anytime you want to deploy an application, anytime you want to deploy an application, anytime you want to deploy an application, you want to interact with, you have to, it's all coupled together. And this guy comes with relational algebra, right? So it's a relational algebra that models so it talks about relational algebra. What was his research about? Data independence, right? Relational algebra, right? Algebra that, okay, yeah, we have to define some set of things that, okay, we don't have to manually interact with the database, right, on the database level, right? And that's where a relational algebra comes into play. And what was his proposal, right? What's his proposal? Data independence, right? That's what it's trying to tell us, that, okay, yeah, we have to ensure that we the structure, right? Structure, and that's where the instead of just everything just coupled together, he had to do it in a relational, like as relations,
a couple
right?
of people, right?
So,
a couple of engineers, whenever there's a change to the data at the physical, they have to change, redeploy, and all. So it proposes a relational algebra. This is proposed about data independence, right? This bring about integrity, say data independence, and structure, right? So those are the three things that Edgar proposed, and it's based on relations, right? On relations. So the database is the database is composed of relations, right? So each relation. So for example, let's say in a school database, right? It's like a university database, right? University database. We have something we call students relations, right? Students relation. We have course relation, and course relation. Semester. Is it fall? Is it summer? Is it spring? So these are the relations, right? This that's what the relation is all about. And he proposed that, so with this Edgar solution, with Edgar solution, you don't have to rely on making changes to the DBMS, right? You don't have to make changes to the DBMS, right? When changes to the physical layer, layer of the database, right? The database when making changes, right? When making changes to the application. So, and one of the things that happen is that, so the logical layer, the physical layer are separated. And one of the things that happen is that, Edgar, one of the things is that you don't have to change the data, right? The DBMS will optimize itself, right? If there's any query change, right? So advantages of third called Edgar approach. Well, what are the advantages of this approach? Of this approach. Number one is the decoupling of the physical and logical layer of the DBMS, right? So, and also number two is that the DBMS optimizes itself when the structure of the data changes, right? Workload and query changes, right? Query changes. So and that's where we optimizer, right? Query optimizer. So all these things are built into the DBMS and make life easier for the application developer. The application developer does not really have to know much about the internal details. Application developer does not really internal details and implementation. That's one of the things that, so the DBMS handling query optimization and all those kind of stuff on itself, right? So that's one of the gains. And then now to I'll attach a paper, detailed code paper, right, for you guys to read, right? And also so relational algebra. Okay, before relational algebra, I want to talk about the languages of the DBMS, right? Of the database, right? Languages of the DBMS, right? So we have data definition, right? Data definition language. We have data modification language. We have data definition, data modification, data transaction control, right? Transaction control language, right? So data definition is more like you want to say create, right? Data modification, right? Update, and transaction start, and then so these are the languages of the database, right? And also data definition, data modification, and also let's go to relational algebra. So what is relational algebra? We mentioned earlier that Ted Code is a mathematician, right? He's a mathematician that at IBM, and his work is more of building. We noticed that application developer have to change the database and the application at any point in time where the structure of the DBMS changes, of the data in the DBMS changes, and this is strenuous, right? So he figured out a way that let's build these things based on relations, right? And we can build up from there. So he proposes a solution, and then based on their structure, integrity, and data independence, and then relational algebra. So one of the things is that there are a couple of operators, right? Couple operators for data manipulation. So, and also data manipulation, definition, and all. So it's just more of some like the mathematical layer on SQL, right? So let's try to separate that fact. So this is the mathematical layer / foundation on which SQL is developed, right? So that's relational algebra in one word, right? And now we have operations, we have select, right? We have project. So relational algebra operators, right? We have select, we have select, we have select, we have project, we have join, we have union, so and all. So now remember, relational algebra is based on sets, right? Mathematical sets, right? Mathematical sets. You remember I mentioned that this is the mathematical layer of which, and also SQL is based on bags. One of the important distinctions is that bags allows duplicate, but this mathematical set by default does not. Mathematical set duplicate. We need to let that be sure. So yeah, now how do we work with relational algebra? So for the sake of learning, I built a visualizer where you can work with relational algebra relations, create a relation, and then do data manipulation, data updates, perform these operations on them. So I built a visualizer on https e-learning.myke.pro/relational algebra for your learning, right? For you to learn, and for learning these things. I will do demonstration on this code for you to see. So yeah, let's go. So this is A, and yeah, the point. This is the guidance of the relation. The relation is more like a table, right? The relation is like a table. You create a relation. After a relation, you perform the expression mode. You can write the expression. I'll show you the expression. Select the symbol. The symbol is very hard to type in the Word, so that's what I'm using here. I created this for you, right, to learn these things. Expression mode, you can write the expression and then it will show you the visual. It will visualize it for you and then show you the result. We'll go through everything. Choose a challenge. There are a couple of challenges on the platform as well for you to learn and get used to these things. And also you can connect to your workflow, or you see that this thing is changing, you want to change the way the data is moving, right, to make it more interactive. So there's a canvas, and also you learn from the output. Yeah. So this is select is very hard to get these symbols, right? So student is a relation. So let's say we have a relation. We can add a relation here on this button. Let's say we have a relation student. I mentioned the university database as an example the other time. Let's say you have a relation called students, a student table. In this student table, you want to select, that. Okay, select star, right? That star means like you want to select star, you want to select everything. Where that's a condition, the predicate, right? Where age is greater than 20, where student status is active, where CGPA is greater than 150, right? 4.0, right? I mean, in Nigeria we use 5.0 on our scale. 5 is the highest, right? So yeah, where students CGPA is greater than 4.0. So here, this symbol means you want to select, right? You want to select, and what's the predicate? What are you using, right? One, which relation? Student relation. So this is basically a select statement. So this is equivalent to. I'm coming. Let me copy it and show you. This is equivalent to this. Is equivalent to select star from, right, from students where age is greater than or equals to 21. So this is the SQL, and then this is relational algebra, right? So basically these two, right, are what we are looking for, right? So yeah, I want to show you build graph. how to use it. You build the graph and it will show you. So this is, you can see it's showing select. This is the relation, student relation, and then it's passing through a filter where the result is just students where their age is greater than 21. One step one of the timeline, and then step two. So you can still step. So one of the beautiful things about this visualizer is that it has a step visualizer. You can, okay, yeah, I want to know what happened on each step of this, of the workflow, right? So at this point you can see it's the student, the student's node. Before we apply the filter, the select, the predicate, age is greater than 21. Before we apply it, you can see 22, 20, 19, 24, 20, even 19 is still there, 20 is still there. We don't want that. So after you can see that after the age now, the result given from the table is Myke with age 22 and Toby with age 24, right? What are the missing age now? Adam and Zainab has been removed from the result. So this is what basically the SQL is doing for you, right? But you don't care about it as a software engineer, because I mean you don't really want to care about how DBMS is operating these things, and you want to care about your application, using the data and then building what you want to build, right? So that's one of the things. And also, yeah, projection. Instead of selecting all the so projection, this is select relational algebra, right? You can do project. What is project? I don't want to project all the data. To show the user select user all the data, then I can do, sorry, there's, okay. So now this is telling me that, okay, instead of selecting star is a universal that, okay, select everything, just bring everything. Now you want to say that, okay, select name from, name, name, you do it this way. Select name from student where age is greater than or equals to 21. What this is telling us is that, okay, after selecting the age, the data that is most important to me is the name. I just only want the name, right? Okay, in the class, or where in our university, we want to know the number of students where the age is greater than 21, right? And then we want to see their names. This is example of a query. Projection, right? Projection. And also, I want you to play around. I'll drop a link on the YouTube channel. You can see the workflow. It selects first, then on the selection, you now perform projection. Let's try to see what it looks like. So after the selection, you can see now. Initially at this stage, the after was 22, 24. But after, you can see after projection, it is just Myke, name, just Myke and Toby. And also I can still include age as well, right? So, and you see it's showing me, right? So please go ahead, work on, try to play around, right? Create relation, add selection, add projection, add join, demo, right? And so this, I have a couple of students and courses as well. So this is a more a six stage pipeline, right, for you to learn about this, right? So I built all these from scratch for your usage and your learning. Please do make use of it and let me know what your what you think about it, right? So yeah, that's it. see. Yeah, so that's it about relational algebra, and also, yeah, I want to mention something, right? I've been waiting for the opportunity to talk about this for a while. That databases are ubiquitous, right? Databases, databases are everywhere, right? Everywhere, right? You see them if you go to the mall, you go to the gym, your phone, right? Your phone, your mobile phone, mobile phone. They use DBMSs, they use databases, right? So DBMSs, I know phones, all phones, most phones use SQLite, right? SQLite, right? As a database in which they handles your storage devices on the phone, right? So yeah, Apache Pino, Apache Pino, Apache Pino, Apache Pino, Postgres, PostgreSQL, PostgreSQL, MySQL, and then MongoDB, and all. So in later next video, right? Next video we'll be talking about. Next video we'll be talking about. Talking about type of databases, right? We'll talk about OLAP and OLTP, right? Why do we have these things? Why do we have a different type of database, right? So one of the things that I want to mention is that we have different databases because of their use cases, right? One is that the workload, right? The amount of workload you want to do, right? Is it a small workload or a heavy workload? That's one thing. One of the things you want to do is it that you want to perform transactional query or you want to just do analytical workload, right? We'll talk about this, and then the file organization, right? That will be next week. How file organization is done, right? Analytical storage, row store, right? So row store, these are industry terms, right? Industry terms, and for their equivalent academic terms, DSM, data DSM, that's decomposition storage model, and then n-array, so n-array, like NSM, that's n-array storage model. So the way they store data, right? We'll talk about this next time. I hope able to let you understand a little bit of data models, Edgar algebra, and to let you know that databases are everywhere. You use them in every day, in every software you're using databases, right? And that's it. We get to talk more in the next video. Bye bye for now.